All right, we're rolling. Okay, hang on. Are we rolling or are we paused? No, we're rolling. Okay. All right. So, thank you very much. Okay, we're not going to go through these limits kind of one at a time. We'll kind of just deal with them as they pop up in the examples. And to be honest, I don't know if we even get to number 7. The limit laws are something that you kind of work with. You kind of understand how limits work as you start to use your algebra methods on them. And eventually, if you ever take something like a number theory course at the university level, you'll probably have to learn how to prove that all these would be true in all circumstances. But that's a little beyond us. For us, it's much more functional. These rules are just how we work with limits. So you should already have this piece of paper. Limit laws continues. There we go. So look around. There should be 6 examples on there. I think I handed it to you the last time you were here. So can you check to make sure you have this piece of paper, and then we'll get started? Okay, anybody not have this? Because I probably have 1 or 2 extras. Okay, this isn't the one on your desk. The one on your desk is for Monday's lesson. This one I handed out, I want to say Wednesday you got this one. Yeah, that's the one. You got it. Okay. All right, so every single one of these 6 examples has something in common. You can use your algebra tricks, your algebra methods, to get around the fact that if you just plug the number that you're finding the limit of in, you're going to end up dividing by 0, which of course is not allowed. So you can see it in the very first example, right? If you plugged in a 2 for that x, you'd have 0 divided by 0, which is not a number. So what can we do about it? Well, some of you probably noticed right away that this thing factors. So I would write this as the limits as x approaches 2 of x squared plus 4, x squared minus 4, all over x minus 2. And then the difference of squares factors again. The sum of squares doesn't factor, but the difference of squares does. And right there is where you can do a cancel. All right. And we'll take a little break for O Canada here. And okay, we're back. All right, so let's finish this example off. Come on. There we go. Okay, so now that that denominator's been canceled, it isn't there anymore. I don't need to worry about it. So now I'm going to turn this to 2 squared plus 4 times 2 plus 2, right? Notice that I don't have, I think I pointed this out the other day, I don't have this on here anymore. As soon as I plug in the limit value, it isn't a limit anymore, it's just a value. Okay, so make sure that makes sense to you. And at the same token, if you forget from one step to the next to put that little limit there, that is a communication error. That is something I'm supposed to take off marks for, because at the university level they will take off marks, right? A limit is a limit and an equation is an equation. The two things aren't really the same. You turn the limit into an expression when you substitute the number in, and then it's not a limit anymore. Okay, so with that in mind, let's finish this guy off. 4 plus 4 is 8. 8 times 4 is 32. So even though this thing doesn't actually have a value when x is 2, it kind of does still have a limit. And that limit is the value 32. If we were to look at the graph of this thing on Desmos, which we can pull up right here. There we go. Notice that when you divide an x to the power 4 by an x, you're going to get some sort of an x cubed. So that does look like a cubic graph, and I guess I have to shrink it a little bit more. And let's see, so when x is 2, it's way up here. So again, if I try, I don't know if you can see that, if I get closer and closer to 2, hang on, a little bit closer and closer and closer to 2. Oh, I'm over it. And it will put a hole there to show you that it doesn't actually exist. It's really hard to get right on it. There we go, undefined. So there is a hole there. But as you can see, the number actually does get closer and closer. The closer you get to that 2, the closer you get to 32 from the top or the bottom. Okay, so there's that one. Go back to the home on that. And back to my notes. There we go. All right, for the next one. Okay, we did one sort of like this the other day. What are we going to do with that? Well, we're going to use our property of 1. We are going to multiply the top and the bottom by the same thing. And in this case, that same thing is going to be the conjugate. That's a plus. Conjugate of that radical statement in the numerator. Remember, my goal here is to make that x in the denominator go away. To somehow come up with an equivalent expression that won't have a divide by x as a factor, because you can't divide by 0. So the top is, of course, first times first. Oops, oh, look what I've already forgotten. Limit as x approaches 0. First times first is x plus 4. Outside times outside and inside times inside are going to cancel. You'll get plus 2 times the radical minus 2 times the radical, and then minus 4 all over. And I'm not going to bother multiplying this out. And you can kind of see why I'm not going to multiply this out if you kind of look ahead by a step or so to see how it's going. All right, can you see where this is headed? The 4 minus 4 cancels, becomes 0, and then I'm left with an x divided by an x that's just 1. So I'm left with the limit as x approaches 0 of 1 over the square root of x plus 4 plus 2. So this expression here is equivalent to this expression here. How do I know it's equivalent? Because all I did was multiply it by 1. So it didn't change what it is, right? But the advantage that the second one has is that the second one won't divide by 0 if I plug in a 0 for x. So that means I can actually evaluate my limit now. So that's 1 over the square root of 0 plus 4 plus 2, which is 1 over 2 plus 2, which is 1/4. The logic of that making sense? So let's take a look at what that looks like graphically. What does this thing look like? Can you kind of picture in your head, what does a square root divided by the same variable end up looking like? Okay, well, square roots tend to be sideways parabolas. If they don't have a plus or minus in front of them, it's just a half of a parabola. But what happens when you divide that half parabola shape by another x? Any idea? As you do more and more of these, you'll start to kind of get like a sense before you even look at it of what the graph might look like. So let's take a look. What does this graph look like? Okay, so that's number 1. Let's take a look at number 2. Interesting. So it's kind of like, sort of starting out like it's a half a parabola, but then it kind of flattens out more than a parabola would. And that's the effect of dividing it by x. Now, what did we say? What happened in our work? We found out that the limit as you approach 0 was actually 1/4. So let's see if that's true. As we approach 0, okay, hang on, approaching 0, approaching 0, approaching 0. Of course, again, when I'm on 0, it's going to say undefined. It's really hard to hold that. Well, you can kind of see that it's happening. Anyways, you can see 0.254, 0.253, 0.252. I'm definitely approaching 1/4. In fact, if I get that close, it rounds it to a quarter for me. And if I approach it from the other side, same thing happens. 0.3, 0.23, 0.24, 0.246, 0.247. We're definitely approaching the value of a quarter, even though when we're on 0, we can't be a quarter. In fact, we can't be anything. Okay? All right. Let's try the next one. Oh, the next one, actually, we're going to switch. When we put these notes together, we realized that this one's actually, we're kind of not ready for this one. This one, actually, I'll spoil it for you. This one doesn't work. This one, no matter what algebra trick you want to pull on it, you're not going to find an actual limit, because all the ones that we've had so far, the limits exist even though the point itself doesn't exist, because the point is a hole. The point is an undefined place in the graph. This one's undefined as well, but it's undefined for a different reason. It's not a little hole, it's an asymptote. So we're not ready for asymptotes yet. So we're going to actually cross this one out. We're going to replace this one. So on your notes here, we'll do ones like this later on. Actually, in the next lesson, we'll do ones like this. Come on, pen. So cross that one out. And let's replace it with one that has a different skill I want to look at. Rational algebra. Okay, once again, because there's that x in the denominator, if I substitute in the 0 for the limit, it's not going to work. I'm going to be dividing by 0, and I can't do that. So I want to, again, use whatever tool is in my arsenal of algebra tools to see if I can get that x to get canceled. And the first thing I noticed is that I have a bunch of fractions, so why don't I try using my fraction skills? What if we turned this entire numerator here into a single expression? So that's the goal. So do you remember how you do that? You do that by working with a common denominator. So the common denominator here is 2 times x plus 2, which means I'd have to, and here I'll write this out in gruesome detail for the first time. I'm going to times this one by x plus 2 over x plus 2. Again, that's the property of 1. I'm not changing what it is. And I'm going to times this one by 2 over 2. Right? That didn't change any of the expression, because all I did was times parts of it by 1. Okay, what's that going to equal? That's going to equal the limit as x approaches 0 of x plus 2 minus 2 all over 2 times x plus 2. And if you're wondering, why isn't he bothering to multiply out that denominator? Why not get rid of that bracket? Well, until I know it's an advantage to do it, I'm not going to bother, just in case something pops up that cancels one of those factors. So does everybody get how I went from the left to the right? For those of you who did grade 11 last semester, this was chapter 6, right? Algebra with rational fractions and fractional algebra. Anybody in the course here who grade 11 was last year? It's been a while since you've seen this kind of algebra probably, okay? All right, any questions on how I got from there to there? Check. I've got my guys at home, you can play along too. I've got my eye on the chat if you need to ask me any questions. All right, so that's going to be the limit as x approaches 0. These 2's cancel, and I have x over 2 times x plus 2. Right? Again, I'm not going to bother multiplying that out. But now think about this part. Think about dividing by this x. Okay, when you're in fractions, divide is the same thing as multiplying by a reciprocal. So what I'm going to do is I'm going to multiply by the reciprocal of that denominator. And then look what I can do. There it is. We have accomplished our goal. Our goal was to not have that x as a denominator, and we don't anymore. Isn't that nice? It's now 1 over 2 times x plus 2. I can plug in a 0 for x now, and I'm no longer dividing by 0. So that's what I'm going to do. So now, once I actually plug the number in, I don't consider it a limit anymore. I consider it a value. 2 times 0 plus 2, which is, again, 1/4. That's a popular answer today. Question? Okay, this whole thing divided by x? Yep, I see what you're saying. This whole thing divided by x, come on, pen. This whole thing divided by x is right here. Right? Instead of dividing by x, I'm multiplying it by its reciprocal. because that's how you would learn in grade 8 how to divide when you're in fractions, right? Instead of dividing by a fraction, you times by a reciprocal. Okay, let's take a look at this thing on a graph. On my graph, that's this guy. Well, it's kind of one of those 1 over x graphs with the 2 arms. And as I approach, what was I approaching in? I was approaching 0. So as I get closer and closer to 0, freeze that. Getting closer and closer to 0, yeah, 0.3, 0.3, 0.29, 0.28, 0.27, 0.26, 0.25, and if I were to get all the way right there, of course I'll get undefined, but as I get infinitely close to it, I get infinitely close to 0.25, which is a quarter. So yep. And feel free to make these graphs with Desmos if you're ever doing your homework and it's like, I don't know if I got this limit right. I mean, obviously you can look at the answer key. I think pretty much everything I assign you will have an answer key. But you can use Desmos to double check to see if you're doing things right. All right, flip over the page. Got a couple more here. I'll give you a minute to see what you make of this. See if you can see what's going on here. Question? Yep. Okay, guys, I'm going back because somebody wants me to go back to the work here, but please give number 4 a go. There. There's the whole thing.
But the thing where you did limit of x0, 1, 2, 2, you said not to write the limit if you're getting rid
Yep.
of
Once you have made the decision that I don't, once I made the decision that I can actually now put this value in for my x, I no longer need this notation because the actual, you've changed from a limit statement to just a value statement, and you no longer need the limit. So that's when this thing disappears. As soon as you plug it in, you don't call it a limit anymore, because it's now a specific value.
So it doesn't matter what you cancel out?
Doesn't matter what I cancel out? I'm sorry, I didn't understand the question.
Okay. Yeah, thank you.
Okay. There are asymptotes in equation 3. Yeah, you're right, there is. But the question from home is, I crossed out this equation. I scribbled out the one that was originally number 3 because I didn't want to deal with an asymptote. I guess maybe I should have said that more succinctly. What I meant was, I didn't want us to approach the asymptote with my limit. So yeah, there is an asymptote number 3, but the asymptote's way over here. And I'm not approaching that number, right? I'm not approaching -2 for my asymptote. You're right. In fact, you can see it in the graph too. The asymptote at -2, come on graph, is right there. As you can see, there's an asymptote line going up and down there at -2. But I wasn't putting in that -2 as my limiting value. And I wasn't going to do that in this assignment because we'll tackle stuff like that later on. Good eye. Good thing you did notice that there is definitely asymptotes in the third one, but that's not what I'm working on. And there's also horizontal asymptotes, but we'll talk about those later on. For right now, we're just looking at limiting values in the horizontal direction and not worrying too much about the fact that there might be horizontal asymptotes. Okay, so did you get anywhere with number 4 while I was talking to people? Okay, it's a kind of what I call the toughest of the 3 types of factoring in grade 10. Right, the 3 types of factoring you do in grade 10 is just look for a common factor, and then factoring trinomials by, I guess, inspection. And this one I call factoring by decomposition, right? You can decompose this one. I might even just do it on scrap paper. So if I have, oops, and then I might try to write with the highlighter. Hang on, get rid of that. There. If I have 2x squared minus 5x minus 3, I can pretty much factor this one by inspection, but let's pretend I can't. I look at this and go, okay, 2 times -3 is, of course, -6. And I want to decompose this term here into something that adds to make -6, but the two things that add multiply to make negative 6. Or sorry, they add to make negative 5. Let me say that properly. But together they multiply to make this negative 6. So the factors of negative 6 would be that would add to make negative 5 would be negative 6 and positive 1. So I'm going to decompose minus 5x into minus 6x plus 1x. Then I'm going to do what's called partial factoring. I'm going to partially factor this by factoring this part and this part separately. In this first part here, I can factor out a 2x, leaving behind an x minus 3. And, well, there's nothing to factor out of this part, so I'll just say I'll factor out a 1, leaving behind x minus 3. Then I factor x minus 3 out of both of these two terms here. And there's my factoring. So you might want to think about doing that on scrap paper. Oops. And then going back, and let's put the limit down. The limit as x approaches 0 of x minus 3 and 2x plus 1. And there we go. Okay, now, notice the x minus 3's cancel. And I get 2x plus 1. And I can plug in the 0. And can I point out to you that actually I could have actually avoided all that work. I could have even avoided that factoring. Actually, did you notice maybe when we started that 0 for x won't be non-permissible? And I don't know if I spelled permissible right. No, I didn't. I got permissible. Permissible? I'm not a good speller. Notice that if I plug in an x, I don't get divide by 0. So did I have to do all this algebra? Well, let's see. What if I just took the original equation and what if I just plugged in the 0? I'd get 2 times 0 squared minus 5 times 0 minus 3 all over 0 minus 3. Yeah, that's not going to be a problem. And that becomes 0, that becomes 0. I get negative 3 over negative 3. Oh, look at that. So always look for that. Before you start breaking out your fancy algebra tricks from your toolbox of algebra, do I need to? And in this case, no, I didn't. There was no problem by plugging in 0 for x in this question. But if you do decide you want to simplify it first, like say for example you wanted to graph it, it's a heck of a lot easier to graph this thing than graph that thing. So you still have that as an option. You can always try to simplify it using your algebra toolkit first. But in the case of a question like this, where plugging in the limiting value doesn't lead to a divide by 0 or a non-permissible situation or head you to an asymptote, then you are perfectly within your rights to just plug in the number. Okay, this stuff's going to be in my way, so I'm going to just erase this. Okay, somebody's asking me a question in the chat again here. Let's see, what are they asking? For the one we crossed out, is it the limit is approaching 0 from the left? Yes, and that's actually, somebody's asking me, the one that we crossed out is the problem that we're approaching the limit from one direction but not the other, or not getting the same limit as we approach it from the other direction. And yes, that's exactly the problem. And that's why Monday's lesson is going to be all about what we call one-sided limits. So questions like that will pop up in the next lesson. So we were a little premature with that question. All right, let's try number 5. Once again, I think this one I'm going to use my rationalization trick. This one for sure I got to do algebra on. I can't just plug in the 3 because I'd end up with 3 minus 3 is 0 as a denominator. So x plus 6 plus root x, or plus x, and root x plus 6 plus x, which is going to give me the limit as x approaches 3. First times first is x plus 6, and last times last is minus x. And then this is going to be x minus 3 times, oops, I meant to make a bracket, not a line. There we go, bracket. Square root of x plus 6 plus 2. So there we go. And, oh, whoops, hang on, that's a squared. My bad. X times x is definitely x squared, not x. Thanks for noticing that. Okay, now, what am I going to do with this thing? Any ideas? I'm still stuck, right? If I plug in this 3 into the x, I still got a 0 factor in the denominator, so I'm still dividing by 0, so no good. Any ideas what we can do with that? Well, how about I look at the fact that that trinomial on top there, if I were to factor a negative 1 out of it, it would look like this. And now there is this factor when I factor that trinomial. So this is the limit as x approaches 3 of the negative of x minus 3, x plus 2, all over x minus 3, square root of x plus 6 plus 2. Those cancel, and now... Sorry. Y plus 2 again. Here? Oh, wait, did I goof something up?
It should be x, like the square root of x plus 6 plus x, or 2. And then
Oh, yeah, it is. I don't know why I'm writing a 2. You're right. Thank you. Let me fix that. Yeah. Oh, you know why? Because I wrote such an ugly looking x here that I suddenly looked at it and it looked like a 2. That's better. Thank you. All right, so now from here, if I plug in a 3, am I going to get a 0 in the denominator for a factor now? No, I'm good. So I can now switch this over to negative 3 plus 2 all over the square root of 3 plus 6 plus 3, which is negative 5 over the square root of 9 is 3, 3 plus 3 is 6. There we go. Okay. Somebody in the chat said divide by negative 1 when I got to, I guess, this step up here. And yeah, that works too. You can divide the top and the bottom by negative 1. I instead just decided I'd factor out a negative 1. Logically, that's the same thing. Okay? And again, if you wanted to check this one on Desmos, you'd see that the limit of this big, nasty, fractiony looking thing, if I were to graph it, is going to approach 5/6. Unfortunately, Desmos does go to decimals, not fractions. So you have to kind of think about what is 5/6. 5/6 is, I think, 0.83 repeating. So what were we approaching again? We were approaching 3. So as we approach 3, we should approach 0.83 repeating. And yeah, 0.831, 0.832, I think so. 0.833, there we go. 0.833, notice it's not changing from 0.833. There's where it doesn't exist. So yep, we are approaching 0.83 repeating. Cool, cool. Okay, one more. Question? Nope. Good question. We never really looked at number 4 on Desmos. Does number 4 have any holes in it? And the answer is, well, yeah, it does when x is 3. Right? But when x is 0, would it have a hole? No, it wouldn't. Let's see. Let's have a look at that. When x is 0, it looks like it crosses right there at, let's see, is it defined at 0? I think it is. There it is, 0, 1. Okay. But over at 3, it has a hole. I don't know if I can see it or not. My thumb is in the way. Oh, there it is, undefined, undefined. There, you can see it for a second. It flashed on the screen. Very hard to actually make Desmos stop where you want it to. Okay, anyway, let's do the last one. We're getting low on time. Got one more to do. All right, it's another big fractiony one. All right, here's how this one works. Once again, can I just plug in 3 and get on with my life? No, because that makes the denominator 0. So I have to break some sort of trick out of the algebra bag. And I think what I'll do is I will start by making the numerator one fraction. So the common denominator here is 9x squared. So I'm going to times the left fraction by 9 over 9. And I'm going to times the right fraction by x squared over x squared, which is going to give me the limit as x approaches 3 of 9 minus x squared all over 9x squared all over x minus 3. Okay, once again, that doesn't solve my problem yet. Putting a 0 in for x is still going to give me 0 in the denominator. Or sorry, putting 3 in for x is still going to give me 0 in the denominator. But I'm getting warmer. I do kind of notice something. And again, this is one of the key skills of being good at math, is to notice when something notice when you have a move, right? Like a good chess player sees the move that you don't notice, and that's why they beat you. I noticed that if this numerator was x squared minus 9, it would factor to x plus 3x minus 3. So that's what I'm actually going to do. I'm going to factor a negative 1 out of it again. While I'm at it, I might as well change the denominator to times the reciprocal of the denominator instead of dividing by it. And then the limit as x approaches 3 of negative x plus 3, x minus 3, that's an x, all over 9x squared times 1 over x minus 3. And now I am not worried about the fact that if x is 3, I'm going to be dividing by 0 because I've gotten rid of that factor. So I can now plug in my values. So that's going to be the negative of 3 plus 3 all over 9 times 3 squared, which is going to be negative 6 over, what would that be? 6 over 81, which is negative 3/27. And on this one, on Desmos, I'd actually, oh, sorry, not 3/27, 2/27. That's better. Thank you. I don't know what 2/27 is. I'd have to actually punch it on a calculator. So let's see, 2 divide 27, 0.07. So if I was going to check this one on Desmos, I'm looking for the decimal 0.07 as I approach 3. So as I approach 3, how close do I get to 0.7? So as I approach 3, go back home so we can see it. There we go. So as I approach 3, how close do I get? Oh, negative 0.7. So negative is it 0.07, I should say. 0.09, 0.08, 0.07. As you can see, we're pretty close. There it is, undefined of the whole. Yep, 0.07 looks pretty good. 0.074 actually is what it says in my calculator when I go 2 divided by 27. So yep, we got what we were supposed to get. And that's the examples we're going to go through today. Here, let me put this back for you. We got about 2 minutes before the band people got to run. Minute and a half. All right. I'll stop my video. That's as far as we need to get to today. Okay. Thanks for watching.